So last time we've seen derivations, so let's recall what a derivation is. So if we have a field extension L over K, then a derivation is just a K-linear map from L to L if it satisfies the product rule, namely d of A times B is A d of B plus B d of A. Okay, that's what a derivation is. Then we saw some first properties, namely that the derivation is 0 for all elements in K, and also that if we have a polynomial with coefficients in K and we have an element in L, then the derivation of f evaluated at A is just the formal derivative of f evaluated at A times the derivation of A. Okay, and now we will generalize this A a little bit, and then we'll see a little bit more about derivations. So this still belongs to this lemma, so let's add some new points. Namely, let's define C equal to be the kernel of this map, of this K-linear map. So we can define a kernel, so that's just the elements in L such that the derivation is 0. And the claim is that this is an intermediate field of the field extension. And now what are the other claims? So let's take an element in L, and if this element is algebraic and separable over K, then the derivation is 0. And now the last claim is that if L is a finite extension of a finite field, so let's say of FQ, then the derivation is just a 0 map. Okay, so we can prove this now by using part A and B. So now we want to show that this is a field, that it's an intermediate field is clear because we've already shown that for elements in K the derivation is 0. Okay, now that 0 and 1 are in this field C is clear. For 0 it's clear because it's a K-linear map, and for 1 we have shown it last time, then that the sum of two elements, the inverse of an element, are also in this field is also clear by K-linearity of the map. Now for the product, that's also not that hard, so let's assume A, B are in the set C, and then we just apply the product rule, so we get A d of B plus B d of A, and by assumption d of B and d of A are 0, so also this expression here is 0. Now all what is left to do is to look at the inverse, and now let's say A is in C, and then we get that d of 1, so let's say A is non-zero because we want to show that inverse elements are also in the field, so d of 1 is d of A inverse, which is d of A times A inverse plus A times d of A inverse. Okay, and now we know that by assumption d of A is equal to 0, so this expression is 0. And now we also know that d of 1 is 0 and A is not 0, so we get that d of A inverse. So this is not 0, so this has to be 0. And it's now we've shown that it's a field. Okay, now for part D, this is also not that hard with the properties we've already shown. So let's again A be an L and M A K be the minimal polynomial of A over K. Okay, and what do? Well, we apply the previous we apply part B. So at first we look at this, and well, this is 0, so we get that this whole expression is 0. And now we can just look at the formal derivative of the minimal polynomial, and then we get that this is equal to this by part B. Maybe let me show you again. So part B was if we have a polynomial with coefficients in K, which we have, because the minimal polynomial over K has coefficients in K, then we get this expression here. And well, that's exactly what we do here. And now if A is, here we have it, algebraic and separable, well, we need algebraic to have the minimal polynomial, and if it's separable, then this thing here is non-zero, so we get that d of A is equal to 0, which means that also A is in this field C. So yeah, we can phrase it either by d of A 0 or that A is in C. Okay, and now for the last part, this is immediate if we know that the fact that FQ is a perfect field. So that means that any finite extension of FQ is separable, and then we just apply part D, and so we know that every element in L is in C, which is the kernel of D, so d of A is 0 for all elements in L. Okay, so that's it for this video about derivations. If you want to know more about this, you can look if you find something about differential algebra, and yeah, I guess there's some interesting stuff going on, even though I didn't have a deeper look at topics from this area. And I guess in the next video we'll see a little bit complex analysis. Yeah, so that's it for today. And yeah, have a good time and hope to see you next time. Bye.